Welcome back to differential equations. In the next several videos, we're going to be looking at power series approximations of functions, how we can use power series approximations to solve differential equations that we couldn't solve otherwise, and how we can use tools in differential equations to get a complete power series representation of a function. But before we do that, I think it's worthwhile to take a little bit of time and review the basic ideas of power series. Specifically, we're going to be looking at power series that are created using Taylor or Maclaurin polynomials, but the ideas of power series are things that extend outward. So, first of all, let's remember that a power series is any function that can be written, the sum k goes from 0 to infinity of some sequence ak multiplied by x raised to the k power. So if we know a way of creating our coefficients ak, we can expand them out. Often it's going to be best to leave our power series in the form of the power series, but sometimes it's worthwhile to expand it out. When k is 0, we get a0 times x raised to the 0 power, but anything to the 0 power is 1, so that's just a0 for the first term. And then we'll have a1 times x, a2 times x squared, and so on. So sometimes it is beneficial to us to write out the power series as a summation. Sometimes it's going to be beneficial to us to list out the first couple of terms of the power series. Depends on the context of the particular problems we're looking at. Any power series has what we call a radius of convergence. And we'll generally represent the radius of convergence as capital R. If the opposite of R is less than x is less than R itself, the series converges. And if x is less than negative R or x is greater than positive R, the series diverges. And in your study of calculus, you learned how to identify a radius of convergence. We even talked a little bit about what happens at those endpoints. Sometimes a series will converge when x is equal to R. Sometimes a series will converge when x is equal to negative R. Sometimes it will converge in both places. Sometimes it will converge on neither place. For our purposes, I'm not going to worry about that. For the purposes of differential equations, I'm just going to assume that the series is going to converge in the space where it is useful to converge. It's not very mathematical of me, but most students taking differential equations are going to be moving onward to study physics or engineering. And in those disciplines, this kind of logic is incredibly important. If you are looking at a situation that models something in the real world, then your equations have to be well behaved for those situations. When we're talking about radius of convergence, If you are modeling something that is a block, a beam in a building, then your coordinates might be that x equals 0 is right in the center of the beam, x equals negative r is where the beam attaches on one side, x equals positive r is where the beam attaches on the other side. And so there's a very physical understanding of, as long as you're within that radius, you're talking about something that's happening to the beam. If you go far enough out that you're looking at where the beam attaches to a wall, well, the math might be a little bit different there. And if you try to go off beyond the wall, well, there's no beam anymore. So of course your function doesn't work anymore. And those kinds of practical applications, those kinds of practical limitations are going to be more useful than the mathematical analysis of where is the radius of convergence. So we're just going to assume that everything works nicely and that there is some physical limitation that will tell us when we've gone too far. Right? Although sometimes having x at the center of the beam is not useful. So we can change the center. Instead of looking at x by itself, we can take, I should do this in a different color so it doesn't blend in with the stuff we just finished. We can take the sum, k goes from 0 to infinity, of ak times x minus x naught squared. And so when you look at the radius of convergence, for the original definition of the power series, the radius, the interval of convergence was centered when x equals 0. By just putting this extra bit in, we can shift things over. For our purposes, looking at modeling differential equations, it is almost always going to be the most valuable to have x naught be the point where initial conditions are given. If you know what your initial conditions are, then they're evaluated, right? Y of x, y of 0, x naught equals 0, that's where our center is going to be. And our initial conditions are almost always going to be at x equals 0 or at t equals 0. So that's a good place to stop with radius of convergence and center of the power series. It's always going to be where the initial conditions are defined. The initial conditions are almost always defined as 0, so we almost never need the more complicated version of the power series formulas. When it comes to working with power series, our goal is to find a power series which is equivalent to the differentiable function f of x. And as has often been the case in differential equations, we're going to implicitly assume that all of our functions are differentiable as much as we need them to be. So we're going to assume that we can take the derivative, we can take the second derivative, we can take the 10th derivative, we can keep going as long as we still need derivatives. And the tool that we're going to use to find the power series equivalent for a function is the Maclaurin polynomial. Remember that the Maclaurin polynomial and the Taylor polynomial behave very similarly. The Taylor polynomial is defined with a center somewhere other than 0, It is a Maclaurin polynomial when the center is at x equals 0. Other than that, they are the same thing. Chances are very good that if you encounter power series approximations for functions in some future course, they're going to call these Taylor polynomials and Taylor series instead of calling them Maclaurin polynomials and Maclaurin series, because Maclaurin keeps getting forgotten. I don't want to forget about Maclaurin, so that's why I am reminding you that when you're centered at 0, it is a Maclaurin series. So we're going to assume that we can write f of x approximately as a naught plus a1x plus a2x squared plus a3x cubed plus so on and so on. I'll show you this far in, and hopefully the pattern will start to make sense. But I want to remind you not just how we do this, but where it comes from. If I plug in that x is equal to 0, on the left-hand side of this equation, I get f of 0. On the right-hand side of this equation, I get a naught. So finding the first coefficient is as simple as plugging x equals 0 into your function. For the second coefficient, we have to start getting a little bit creative. And the creativity we're going to use is to take the derivative, f prime of x. Well, the derivative of a constant is 0, so the first term goes away. Then we're left with the second term, a1 times x. The derivative of a1 times x is a1. The derivative of a2 times x squared is 2 times a2 times x. The derivative of a3 times x cubed is 3 times a3 times x squared. And you can keep going. But now that we've done this, we realize that the same thing we did to find the first term, once we've taken the derivative, works to find the second term. F prime evaluated at 0. You get a1, and every other term has a factor of x. Multiplying by x equals 0 makes the term go away, so a1 is the only term that survives. At this point, you start to get cocky and think, oh, I can just take derivatives and evaluate at 0, and that's all I need, which is almost but not quite the correct thing. Because if we look at the second derivative, right, a1 goes away. The x term, derivative of x, is still 1. But instead of having just a2, we have 2 times a2. And then in my third term, I've got 3a3 times the derivative of x squared, which is 2x. Right? For the sake of explaining the pattern, I'm going to write that as 3 times 2. I know that 3 times 2 is 6, but it's worthwhile to have that as a pattern. So that f double prime of 0 is equal to 2a2, which means that a2 itself is f double prime of 0 divided by 2. And then I'll do one more of these. The third derivative, f triple prime of x, is equal to 3 times 2 times a3, and a bunch of other terms, and the other terms are all going to be 0 when x is 0. So when I evaluate f triple prime of 0, I get 3 times 2 times a3 by itself. And rearranging that gives me that a3 is f triple prime of 0 divided by 3 times 2. You can keep doing this. The pattern absolutely does continue. In general, instead of trying to go through this one by one for perpetuity, in general, the rule is that if you're taking the nth derivative and evaluating at 0. Remember, whenever we go beyond the third derivative, instead of continuing to put more primes in, we put the parentheses and the number of differentiations that take place. So f parentheses 4 is the fourth derivative, f parentheses 5 is the fifth derivative, in general, the nth derivative here. And then you divide. For a2, we had to divide by 2. For a3, we had to divide by 3 times 2. Looking at that pattern, for a4, you probably will have to divide by 4 times 3 times 2, and so on and so on. In general, that is exactly the meaning of factorial, right? N factorial means multiply. N times n minus 1 times n minus 2, and keep going until you get down to 3 times 2. I haven't multiplied a times 1 explicitly, but multiplying by 1 doesn't change anything. And so that gives you that denominator. And so that is the general form of, excuse me, that is the general form of the coefficients of the power series based on the Maclaurin polynomial. As long as the function is continuously differentiable, you can take all of the derivatives, you can compute all of the coefficients and get the expression for the function. There are a couple of functions whose power series representations you should be familiar with already. The function e raised to the u power is the sum, k goes from 0 to infinity, one over k factorial times x, no, I'm using u's, u to the k power. If you have just x or just t, that's easy. If you have something more involved, it's still not that bad. The power series for cosine of u is the sum, k goes from 0 to infinity, of -1 to the k power divided by 2k factorial times u to the 2k power. The power series for sine of u is the sum, k goes from 0 to infinity, of -1 to the k plus 1 power all over 2k plus 1 factorial times u raised to the 2k plus 1 power. Slide those over a bit to make room for a couple more. The power series for natural log is probably the weirdest of the bunch because natural log of 0 is undefined, so we have to shift things over. Natural log of u plus 1. And also notice here that the k equals 0 term does not appear because, of course, if you tried to plug in k equals 0, you would be dividing by 0, which is undefined. So we start the natural log, which has u plus 1, not u as its argument, with k equals 1, and the summation continues from there. I've also listed the power series for the hyperbolic cosine and the hyperbolic sine, which are almost identical to the power series for cosine and sine, except that the oscillating term, the -1 raised to a power, does not appear. Of course, you are probably familiar with other power series of other functions. We can find a power series for a function in general, But if you know those six, you know just about everything that we might need to use for the purposes of this course. To give you some review of where these formulas come from, let's take a look at one other power series. F of x equals 1 over 1 plus x. Again, not just 1 over x, because 1 over x is undefined when x equals 0, and I'm looking for the Maclaurin series, the series centered when x equals 0, which means that x equals 0 had better be defined. But if I plug in f of 0, I get 1. And then if I take a derivative, f prime of x, differentiating 1 over 1 plus x, I guess that instead of thinking about it in those terms, thinking about this as 1 plus x to the negative 1 power will make the process make a little bit more sense. I'm going to have the negative of 1 plus x raised to the negative 2 power. And when I plug in x equals 0, 1 plus 0 is 1, 1 raised to any power is 1, and I get f prime of 0 is negative 1. Taking the next derivative, I will get 2 times 1 plus x raised to the negative 3rd power, and when I evaluate this at 0, I'm going to get positive 2. If I take the third derivative, I will get negative 3 times 2 times 1 plus x to the negative 4th power. And evaluating this at 0, I will get that f triple prime of 0 is negative 3 times 2. And yes, I know that 3 times 2 is 6. I could simplify that. But writing it out like this and seeing where the pattern is going to show up is going to make our lives a lot easier. I'm going to do one more before I start trying to identify the general pattern. The fourth derivative of x, well, multiplying by negative 4. We already have a negative, so negative times negative is positive. 4 times 3 times 2 times 1 plus x raised to the negative 5 power. And if I evaluate that at 0, I get 4 times 3 times 2. I think that that's far enough to see where the pattern is going to show up here. If I am taking the nth derivative, well, in front, I'm just going to keep multiplying by each successive power. So all told, that's going to be n factorial. Then I'm going to have 1 plus x raised to a power, and my powers have just been descending. But they're always one off of where I started. Right? The first derivative had the negative 2nd power. The second derivative had the negative 3rd power. So in general, the nth derivative is going to have negative n plus 1. And let's write that in white so that it's more readable. Right? The negative of the n plus 1 power is going to be the exponent there. And then in general, taking the nth derivative and evaluating at 0, that whole thing is going to be 1 leaving me just with n factorial. Except there's something missing here. And I was a little bit sloppy. I didn't leave myself quite as much space as I intended, so let's leave a little bit more space there. The thing that I haven't done is that this is oscillating between being positive and negative. For an odd order derivative, this comes out as negative. For an even order derivative, it's come out as positive. And we expect that that's going to continue to happen. We can represent that by just taking -1 and raising it to the n power. If n is even, an even number of factors of -1 is +1. If n is odd, an odd number of factors of -1 is -1. So either way, we get the pattern that we're looking for. So all told, the nth derivative evaluated at 0 will also have that -1 to the n times n factorial. But that's still not the end of the road, because the Maclaurin polynomial tells us that we can write f of x as the sum, k goes from 0 to infinity, of ak x to the k, where ak is the kth derivative of x, of f, evaluated when x is equal to 0, divided by k factorial. So replacing n with k, we have in this case -1 to the k times k factorial divided by k factorial. The k factorials cancel each other out. And the power series for this function is -1 to the k times x to the k. Again, I'm most interested in working with power series where we can be comfortable in how they work. So for example, using the power series that we dealt with before, if I have a function that's made up of a couple of cosines, say the cosine of 2 pi x plus 3 times the cosine of 5 pi x, I know that in general, cosine of u is the sum, k goes from 0 to infinity, of -1 to the k over 2k factorial times u to the 2k power. Substituting in my particular cosines, where u is 2 pi x or where u is 5 pi x, I can write this as the sum, k goes from 0 to infinity, of -1 to the k over 2k factorial times 2 pi x to the 2k power plus 3 times the sum, k goes from 0 to infinity, of -1 to the k over 2k factorial times 5 pi x to the 2k power, which is perfectly fine on its own, but we can do a little bit better. I can distribute the 3 over the summation and bring it inside. And then I can realize that these two summations can be combined and written as a single summation. So I can take all of the stuff inside the first summation, and all of the stuff inside the second summation, and bring it all together. Then I start noticing that some of these things are in common between the two. Both of these terms have a negative 1 to the k. They both have a 2k factorial. They both have a pi times x to the 2k power. And if I can just split out the rest of this, then I can simplify quite a bit more. And I can just split out the rest of this. Using properties of exponents, 2 pi x all to the 2k power, I can think of separately as 2 to the 2k power times pi x to the 2k power. And then I can use the commutative and associative properties of multiplication to get that 2 to the 2k power out of the way. I did the same thing over here on the second one, taking my 5 pi x and splitting it up as 5 and pi x, and then just using the commutative and associative properties to get a couple of things out of the way. And I need a closing bracket on that still, so let's fix that real quick. Then I can factor out all of the stuff in parentheses. This is going to be the sum. K goes from 0 to infinity of 2 raised to the 2k power plus 3 times 5 raised to the 2k power multiplied by negative 1 to the k over 2k factorial times pi x to the 2k power. And if we can bring that all into one term like that, then we have greatly simplified what we're working on, and we can make our lives easier moving forward. I would like you to try the same process, only this time let's look at some exponential functions. F of x is e to the x plus e to the 2x minus e to the negative 2x. And I would like you to use the knowledge of the power series representation of the exponential function to write this expression as a single power series. See what you can do with that one. I'll see you in the next video.